The topic we're going to move on to in this lecture concerns ultimately quite an advanced area of computer science. So this is the second part of the extensions we need to make to calculus in order to deal with complex valued functions. In particular, we're going to be looking at how integral calculus needs to be developed in this case. So if we're integrating complex functions, we need, as it turns out, quite an extensive range of new technical apparatus. So we saw when we were looking at integration in the context of real valued functions, we can link that idea to the notion of measuring a particular area. When we move to complex valued functions, that is no longer true. We cannot relate integration to this concept of area measurement when we are working in the complex plane. Nevertheless, I thought this would be an interesting topic to include in the module, mainly because the techniques underlying complex integration are of great significance in an important area of computer science, in particular the area of algorithmics that you have been studying on Professor Wong's module Comp 108. And the particular relevance concerns the subject of counting objects with a particular property and relating that to the notion of what the average case properties are. So on Professor Wong's module, you'll have met the idea of looking at an algorithm and analyzing its worst case running time. And in general, that's fairly straightforward. A much more practical, in some sense, measure of how well an algorithm performs, though, is what is average case running time. And measuring the average case running time of algorithms is something that's notoriously difficult. So let's give a little bit more background. Suppose we have a function whose domain and range are the complex numbers, and we take two arbitrary complex numbers. How do we interpret what this structure means? In other words, the integral between those 2 points of the complex function with respect to its variable. Now we've seen already that we can treat this as splitting the function up into an integral involving the real part of that function and an integral involving the imaginary part of that function. The problem we have, though, is our integration bounds are complex numbers. And the complex numbers, as I mentioned, are not ordered. So unlike the real values, we cannot think in terms of some area that's spanned by the complex number between two particular complex values. What we can do, however, is think in terms of moving from one complex point to another complex point in the complex plane. So what do I mean by that? Here's an example. Let's suppose we have 2 points in the complex plane. And intuitively, we can think about starting at one point and moving along some path, some curve, to reach the other point. And we can think about, we're not limited to the case of a path not being closed. We can also think about moving along this kind of path. We travel from here reach our intermediate point, and we travel back again. So these are what are called curves, these are what are called contours. And a very important notion when we look at complex integration with respect to this notion of a path between the limits of our integration is this idea of a parameterized curve. So we move between points by describing the path that we are using and the direction in which we're traveling. So either of those two examples on the previous slide. And when we do this, the integral that we are looking at, we introduce this new notation. Instead of using these bounds, we give the name of the curve that we're going to integrate with respect to. And in the special case, where the curve is closed, in other words, when the limits of our integration involve traveling from a point back to itself, we have what is called contour integrals, and we introduce a new notation for that as well. So what do we mean by all of this? Well, to start off with, we have some interval on the horizontal axis, the real axis. So this starts at the real part of our initial point, and it ends at the real part of our end point. And the way in which we're going to describe moving along a path is we use a function which maps from real values to complex values. And this function has to satisfy particular properties. The first property is if we look at the value of that function on the real number corresponding to the real part of our starting point, the complex number that results is our first complex number, our complex number p. And similarly, if we look at the value of that function on the real number corresponding to the real part of our endpoint, the complex number that's returned is the complex number corresponding to our destination point, our endpoint. And as we've already seen, we can take a function like this, a function mapping from real numbers to complex numbers, and we can split that function up into its real and its imaginary parts. So we can write it in terms of some function corresponding to what happens with the real part, and some function corresponding to what happens with the imaginary part. And what that means is if we take any number in our interval, then the value of the function we're concerned with is just the value of the real part function, this, plus I multiplied by the value of the imaginary part function, this one here. And what we call this is referred to as a parameterization of the curve that's being used. So how does this help? Well, what we can show is if we take such a parameterization, a mapping from the real numbers to the complex numbers, which has the properties we want with respect to the start and the end point, then what we find is that this integral over the path, over the line we're using, of the function of interest, that turns out to be identical to this integral between two real values. In particular, the value of the function on the curve at a particular point multiplied by the first derivative of the curve function. So the important property we have here is the domain of this integral is the real numbers. So this value can be less than this value. We can order these two values. And that means we can just use our standard classical real integration that we met earlier, because we can rewrite this function here just as the outcome that results by integrating the real part function, and we add to that I multiplied by the outcome from integrating the imaginary part function. So here's an example. Suppose we take the complex function corresponding to squaring the real part and squaring the imaginary part. And we're going to look at this over an interval between 0 and 1, these two real numbers. So those are our, and we're going to use that in that interval. The starting points we're going to be looking at are the complex number 0 and the complex number 1 plus I. And the parameterized curve we're going to use is this one here. Parameterized curve which takes a value t and reports the complex number t plus I multiplied by t. And that's between this interval here. And this satisfies the properties we need. If we evaluate this function at the point t equals 0, we get the outcome 0. That's our starting point. If we evaluate this function at the point t equals 1, then we get 1 plus I. That's our end point here. So if we're looking at this diagrammatically, this is the complex plane. This curve corresponds to a line taking us from our starting point, traveling along that line to the end point. So what happens? Let me repeat, we're looking to integrate the function corresponding to squaring the real part and squaring the imaginary part between these two complex values, 0 and 1 plus I. And we're going to use the curve which has a parameterization t plus I times t, which is valid when t is at least 0 and at most 1. So we have to start off, we differentiate this function, and we get just the outcome 1 plus I. And we look at the value of our function, this object, when we apply it to the curve function. And we get that this is the value of the function on t plus I multiplied by t. Our function squares the real part, we get this outcome, and it squares the imaginary part, we get this outcome. And now, if we put all of that into what we derived on the previous slide, if we are integrating this function along this line, then the outcome is exactly the same as integrating between the limit 0 and 1 this function here. And that is fairly easy to check. Is the outcome 2 multiplied by I divided by 3. So that's our complex integration solved for that particular case. Let's look at another example for a closed curve. So here what we're doing, the function of interest is 1 divided by the input value. The region, the interval that we are looking at is again between 0 and 1. But this time the contour we're going to use is e raised to the power 2 times pi times I times t. So this is a closed curve, and what it corresponds to is a circle of radius 1, and that circle is about the origin. So the contour we're using is going to travel in this path here, in a circle. What happens in this case? What happens is we are integrating, remember, the function 1 divided by our complex number, and we're integrating around the circumference of a unit radius circle. And the parameterized curve we're using is this curve here. and it's between the values when t is at least 0 and t is at most 1. So what happens in this case? We have to find the first derivative of our parameterization, and that is just this function here, 2 times pi times I multiplied by e raised to the power 2 pi it. So that's our derivative. We look at the value of our function, this function here, applied to the parameterized function. So that turns out to be the value of our function applied to this. And that, as we can see, is just this outcome here. Now we apply our integration technique. And what we find is that this integral is exactly the same as integrating between 0 and 1, this function, and that turns out to be the integral, the result of evaluating between 0 and 1, this function here. These two terms cancel, and what we are left with is that when we are integrating this function around a circle with unit radius, the outcome is 2 multiplied by I multiplied by I. So I mentioned we are looking at complex integrals. The point of doing so is how they arise in computer science. And I've just given a very basic introduction to the techniques we use, but one of the most powerful applications of these ideas arises in the problem of counting objects of particular forms. So what we're trying to do is we are trying to find what's called an asymptotic estimate for the number of objects of a particular type that have a given size. And the two powerful techniques that are used in computer science, one of these is the notion of generating function, and the other one is a result which is called the generalized Cauchy integral formula. So let's look at the first of these. First of these, suppose we have some sequence of numbers. Then, for example, this might describe the number of objects of a particular size. So this could be something like the number of binary trees with a certain number of leaves, the number of permutations of items which don't change the position of one of the items. And these are problems that often arise when we are trying to analyze the average case behavior of an algorithm. So, first of all, let's look at generating functions. One way we can write these objects is we express what we're trying to capture as some infinite sum, where the object of interest is the coefficient of a particular power. So the coefficient of z to the power n, this is the object that describes the number we're actually trying to count. So how does this help? What we find is if we take this sum relationship as defining a function, then often we can manipulate that sum in ways that allows us to simplify the counting problem. So here's an example. Suppose we go back to our problem of counting the number of binary trees which have a certain number of leaves. And we write this is our generating function for that problem. Well, a binary tree, either it's just a single node on its own, and so we don't have any leaf nodes, or it's some root node, and we have two subtrees, and when we add the number of leaves in the subtrees, we get this value n. So after some manipulation of this formula, I'm not going to go through how that's done using this analysis, what we find is that this function corresponds to this rather complicated looking object here. And what that tells us, we can count the number of binary trees with a certain number of leaves, we can do that by analyzing what the relevant coefficient is in this function here. So how do we do that? Well, one of the tools we can use is this device called the generalized Cauchy integral formula. And this is quite a deep and quite a surprising result in complex analysis. And what it tells us is how to extract this value from some kind of closed form, some generating function for a particular counting problem. Now, one way we could do that is we could take our closed form and we could differentiate it n times and we could extract the value we need as a result. Alternatively, suppose we denote the derivative we're looking for using this notation. Then what the generalized Cauchy integral theorem tells us is we can proceed like this. Let's choose some closed contour. Then the result we want is the outcome of this complex integral here. And so all we need to do is we find this integral and we evaluate the resulting function at the point z equals 0. And that gives us our outcome. So let me just summarize what we've looked at here. First of all, let me stress I have deliberately skipped over quite a complicated amount, significant amount of detail, not only in the case of Cauchy's integral formula, but also in the full treatment of generating functions. If I was going to do that properly, both of those topics would comfortably take up an entire module. Complex analysis is of great importance in a number of specialized areas of algorithmics, in counting, in finding good estimates of hard to count quantities, and in average case studies. So all I've been aiming to do in this section is just to give a basic idea of what these techniques involve.